Okay, hi everyone. So I just thought I would do a clip here where I just talk about uh, what we're learning in this lesson, which is slightly different from what we've worked with before. Okay, because we've been working with derivatives of polynomial functions, or you could say power functions. Okay, and we've been using the rule with x to the n. Okay, if on the other hand we have expressions for exponential functions, such as 2 to the x, or really this could be any positive number here, although we don't normally write 1 actually, but any other positive number, then we would then we have a so-called exponential function, okay? And we would say that it's of the form a to the x, okay? And of course, sometimes we say c times a to the x. If we just have a constant, some sort of constant multiple here, then basically then that just sits there. So we would end up with a situation where if we had 10 times this, we would just end up with 10 times this after differentiating. Okay, so here I haven't bothered with the c, or we can say that it's equal to 1. I've just focused on the a to the x part, and I've just focused on, I've just shown some examples with different values of a here. Okay, so what are the results here? So if this is the expression, then this is the derivative. So you see from the color coding here that we have 2 to the x here and here. So that means the derivative function, it's the same function, except that it's multiplied by this 0.69 here. Okay, so this is our rule in this situation. Now, this might seem a little bit mysterious, but I will explain more later on, and things will start to make more sense. Okay, if we have 2.5 to the x, then we get this. We get 0.92 multiplied by, and then just this exponential term that we started with here. If it's 3 to the x, then we get 1.10 times 3 to the x. Okay, so you can basically just do this with any expression of the form a to the x. And what happens is that for this value, when we differentiate this a to the x, we always get this a to the x here, but we also get this extra kind of multiplier here, this extra coefficient here. And we see that as the value of a increases, the value of this coefficient increases. Okay, so that means that somewhere between 2.5 and 3, there is a number such that this coefficient will be equal to 1. Okay, and it turns out that this property in math is like super important, because basically then we have an expression. It's of the form a to the x. Okay, where we're basically, when we form the derivative, we get 1 times this. Basically, the derivative is the same function as the function itself. So it means that we have a function that that is equal to its derivative. Okay, and this basically is useful in science. It comes up quite a lot, where we want the function for the rate of change to be equal to the original function for the value itself. Okay, so basically, when we have the value of a for which that is true, we call that number e. So this is so-called Euler's number. So it's from a famous mathematician called Euler, that basically, I guess, was one of the main people behind developing all these ideas. Okay, and basically there's a number, it's actually equal to 2.718281828. Okay, even though this part actually repeats, it's not actually a repeating decimal. It kind of changes later on. It's actually a so-called irrational number. So for example, pi, 3.14 and so on, is also an example of an irrational number. Okay, so this Euler's number E, this is a new example. So an irrational number, if we try to write it as a decimal, we get a decimal that goes on forever. That is, we get an infinite decimal, and where it does not repeat, it's not recurring. Of course, there might be some little parts that repeat, but the whole thing, taken as a whole thing is non-repeating. Okay. So you see here, this is what we expected, that there was some value between 2.5 and 3 for which this coefficient is equal to 1. Okay. So basically, this is the number E. So maybe this is okay. Maybe I make a clip here and we say, okay, well, the theme of this film was the number E and an introduction for that. Okay. So I just point one or two things out before we finish. So firstly is that when we work with derivatives for exponential functions, we will not use the definition of the derivative. Okay, we'll be just using it using the shortcut formulas from the formula sheet. Okay, that sort of way. Now, in the book, they try to explain how you can kind of reason using this definition, but their explanation is really a fairly advanced explanation. It's not something we need for our course. And I recommend skipping that and just focusing on the main parts. So I guess the key point is that it is possible to start with the definition and get these results, but that we're not going to do that. Okay. So what was the message here? The message is that now we're going to start looking at derivatives for exponential functions. Okay. And there's this pattern that we're seeing here. So then it's possible to find a number, which we call E, which is roughly equal to 2.7, for which you get the same derivative as the original function. And it turns out that that is a very special property of math. And this is the idea that we're going to be developing further in our next film. Okay, super. So thanks for watching.